action. Let's see if I can do this in one take. I want to talk about waves. I'm going to try and write some stuff down. I'm going to draw some pictures too. Waves. What is a wave? A wave is a transfer of energy through a, quote, medium. A wave is a transfer of energy through a medium. Well, what's a medium? Well, the medium is what the wave goes through. So we can have different types of medium. We could have air, which is what sound travels through. So we've got air, which is what sound travels through. Now, this one's light. We've been talking about light because we've been talking about redshift and all that stuff. Light, well, what is the medium that light travels through? Well, it's actually not nothing. It's the electromagnetic field. Electromagnetic, quote, field. So the electromagnetic field permeates all of space, and that's what light travels through. As it's traveling through space, the medium, there's no medium in space. Space is empty. Well, light is moving through this field that permeates all of space. Now, what the medium does, both of these things, the medium oscillates. Or vibrates. So the medium either oscillates or it vibrates. What does it mean to oscillate or vibrate? It just moves back and forth. So air molecules, if we're talking about air, I'll just draw a molecule of air and it moves back and forth. That's what air does. The electromagnetic field, I'm tempted not to draw what it does, but I'm going to try it out for you guys. This one's a little tricky for me. I'm going to use some different colors. We're going to say that this is the direction that it's traveling in. Oh, wish me luck here, guys. I am going to go like, I'll use red. I'll go like this. Okay, I'm going to go like that. And then for blue, I'm going to go like this. Oh man, that actually came out pretty good, I think. These red ones, this is moving up and down. Oh, Control Z. I got to get to red. These red ones are going up and down. And these blue ones are kind of going side to side. Yeah. And like this. You don't have to necessarily draw this down. But I'm going to keep going because I'm doing a heck of a job, I think. And then if I do this, these guys go down now. This is more like for your information than anything. These guys are going down. These two fields, this field here, that is the electric field. This field here is perpendicular to it, and this is the magnetic field. So this is what oscillates when light moves, and light in this case would be traveling in, let's say, this direction. So that's what moves back and forth. This is like next level stuff, but I just wanted to, well, when we're talking about sound and we're talking about waves, it's the air molecules that move back and forth. when we're talking about light and we're talking about waves, it's the electromagnetic field that moves back and forth. There's an electric field that's oscillating, and that field is oscillating perpendicular to a magnetic field, and they're connected together, and that's why we call it the electromagnetic field, and that's why we refer to light as electromagnetic radiation. It's energy that moves through a field of electromagnetic energy, I guess you could say, which I didn't say very eloquently. But those are the things that are oscillating. So air molecules move back and forth, and they carry a sound wave through the air, or electromagnetic field oscillates back and forth, and that carries the light through the vacuum of space, if you will. I got to slide this over a little bit. I actually have to resize, file, resize. I want to switch my width here to like 4,000. Okay. Control Z. That got crazy. File. Resize. Thanks for your patience, folks. Oh. Okay. That's better. I've got some more room now. What I want to talk about next, waves transfer energy through a medium. There we go. We have this thing called the wave equation. I think I talked about this the other day. The wave equation looks a little something like this. Velocity, frequency, times wavelength. Okay, this is velocity. The V stands for velocity. This is the frequency. Times the wavelength. So I've written it out in symbols. V equals F times, this is the lowercase letter lambda. Lambda, I think it's DA, lambda. I never spell that one right. Well, what's the frequency? Well, the frequency is waves per second. And then the wavelength is distance between waves. And what I've done here, this is actually in a unit Hz. This is called Hertz. And then this, just conceptually, if I was going to draw a picture of a, well, that came out kind of ugly. Draw an oscillating medium. This would be the wavelength here, or this would be the wavelength there. Same distance. It's just the distance between waves. In this case, the tops of the waves or the bottoms of the waves. Units, well, waves per second, it would be number per second times, well, how do you measure length? Well, we measure meters. And you would get a velocity, which is in meters per second, when you multiply those two guys together. So this is our wave equation. It's the relationship between velocity, frequency, and wavelength. Okie dokie. That's how quickly a wave will move through the medium. I want to talk about light now. I don't have too much more to talk about, but I'm going to slide this over here. I'm going to scroll up a little bit so I've got some room. Oh, I want to try and do this right. Where'd it go? I got this. I got this, kids. I want to talk about electromagnetic radiation. Control Z, the spectrum of electromagnetic. What happened? The spectrum of electromagnetic radiation. What I want to try and do is I want to try and do this. Wait a second. All right. I'm going to write this out now. I can do this. This is the rainbow. Roy G. Biv. Visible light. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. If I go this way, light gets redder. So if I'm going that way, light gets redder, more red. If I'm going this way, it's bluer. Bluer, whatever that means, redder, bluer. Well, if I think about this, what I can say over here on the blue side, past violet, I would get to UV, ultraviolet. Eventually, I would get to X-rays. And then finally, I would get to gamma rays. This is the Greek letter gamma. These are gamma rays. So if I keep going this way, if I keep getting bluer and bluer and bluer, eventually you wouldn't be able to see it. It's not in the visible spectrum anymore, but you can consider it to be bluer all the way out to gamma rays. If I go the other way, I get to infrared, I get to microwaves, and then over here I get radio waves. Radio waves way over here. So I've got the visible spectrum in the middle. I've got UV, X-rays, gamma rays. I've got IR, microwaves, radio. One thing I want to do is I just want to kind of sketch out. These are really long wavelength. Radio waves over here. This is really long. Over in here, it's like somewhere in the middle, I guess. Not very big. This is not like precise. This would be lambda here, Control Z, lambda. Now way over this end, we've got really short wavelengths. So really small lambda. There you go. Now, this is kind of a conceptual stretch. Velocity equals, in this case, we're talking about the speed of light, which is c, is equal to frequency times wavelength. That's kind of in the middle. This velocity is constant. C is always 3 times 10 to the 8th meters per second. So when we're talking about light and we're talking about the velocity of light is always the same. So I have to get C over here. And I also have to get the same C over here. The speed of light is the speed of light is the speed of light. In the middle, if I just take my frequency times my wavelength, right, I would get the speed of light. But what happened over here is my wavelength went up. I have a really long wavelength, and I'll draw that large. Well, that means the frequency had to go down, because I have to multiply those two numbers together, and I have to still get the speed of light. So if my wavelength increases, my frequency has to go down. So when we're talking about red light, we're talking about low frequency, and we're talking about long wavelength. Long wavelength. So that's low. This stuff over here is, wait a minute. This stuff over here is low E. So as you go to the red side of things, as you get to the radio waves, that's low energy stuff. Now, if I go the other direction, if I talk about the other side of things, well, my wavelength is really small now. My wavelength decreased, which means my frequency had to increase. So this is high frequency. When we're talking about the bluer light, it's higher frequency light with short wavelength. This stuff here is the high energy. Oop. There you have it. So when we stretch out the wavelength, when we start talking about radio waves, they're really long wavelength, low frequency stuff. I'm getting bombarded with radio waves right now, you know, very low frequency. Not many waves hit me every second because it's low frequency stuff. High frequency stuff, lots of waves hit me every second. And I get blasted with radiation in the form of light, X-rays. So there's a relationship. The high frequency light is the high energy light, and the low frequency light is the low energy light. The bluer the light, the higher the energy. And a way to remember that is you're going to feel really blue if you get gamma rays. If I shine gamma rays on you, you're going to feel really blue because you're not going to be very healthy for very long as you get blasted with that high energy radiation. One thing I can do too, hopefully this will work. If I go over to here, I put a link to a picture, and it's a great visual representation of what's going on. Oops. This shows the spectrum, just like I talked about. I did a pretty good job with my diagram. I've got visible light in the middle. It shows me the wavelength. Gamma rays have 10 to the 1,000,000th of a meter in wavelength. Radio waves are thousands of meters long in terms of their wavelength. The frequency is really what we need to worry about. So when we're talking about red light, the frequency is, 10,000 waves hitting you a second. 10 to the fourth is 10,000. 10,000 waves hitting you a second versus, if we're talking about gamma rays, it's 10 to the 20th, which is like a million. It's 100 million. 100 million waves hitting you a second. And that's why gamma rays are so destructive, because that's a lot of energy. Every wave, remember, a wave is a energy traveling through a medium. So every time a wave hits you, where are people going? People are disappearing. Every time a wave hits you, oh, wait, no, we're good. Yeah, it shares a little bit of energy with you. So when you're getting blasted with 10 to the 20th waves a second, that's a lot of energy versus, 10,000 waves per second. Big deal. There you go. That was my conversation about waves. I hope that worked out.